mechanical energy and other forms of energy like heat energy and solar radiations. And then how directly we are making the devices to be utilized for energy autonomous sensors. So the main point here is we are focusing towards energy autonomy. That means the sensors, they are not going to depend on the electric power that we are commercially using. That means what we are commercially getting is the commercial electric power which is generated from the conventional power plants. So we are trying to generate our own energy by our waste mechanical energy that we are spending from our day-to-day activity. So before going into the topic, let me introduce about our Center for Flexible Electronics. So you all well know about our center, which is in the 6th floor of C block, C611. So our key research areas are flexible energy harvesting devices, in which we are focusing on solar cells, triboelectric and piezoelectric nanogenerators. And we are also focusing on flexible energy storage devices, particularly we are focusing on supercapacitors mainly. We have few researchers working on that field. And batteries, we are trying to establish the battery research facility in our center. And then we are focusing on self-powered sensors and then nanomaterials. Mostly we are working because we have a wet lab, so we have various synthesis techniques to form different synthesis over there. And then nanosensors are also we are doing, as we have a gas sensor setup. We are going for a nanoscale gas sensor as well. And few other sensors that we are also doing along with the self-power capability. So there are 4 key research faculties which we are mostly engaged in our center, and these are all our research scholars. So who are doing their PhD and their research activity and closely associated with our research center carrying out their research activity in the above topics. So each one corresponds to the above topic that they are working with. And these are few of the high impact publications that we got in this last 1 year result. It starts in 2022 August onwards. So until we closely we can correlate, say that in the last 1 year, so we got several high impact publications. Like the best one that we got out is in the nano energy, which is impact factor 17.5, and 2 back-to-back papers we got in Wiley Small 13.5, and Journal of Power Sources, and then JFCP, which we got this month, the beginning of October, I guess, and then Journal of Physics Energy and Journal of Physics Materials also we got recently. This last week this paper got published, and then one in Wiley Energy Technology and 2 paper of this one and 1 from Chemical Physics Letters. So most of the papers focusing on triboelectric nanogenerator and supercapacitors. Yet we have a few more papers which are published, which I list out here. And this last 1 year, this is the outcome from our center with the facilities that we are having. So the agenda of today's talk is mostly we are focusing on the wearable electronics part of it. So in wearable, how we are integrating energy harvester and how we are going for a self-powered sensor. So then autonomous electronic skin-based energy harvester and sensor. Then what is the need for self-powered system in wearable electronics? Then in that wearable electronics, we are incorporating triboelectric and piezoelectric effect, because these 2 effects are the one which can be able to scavenge the ambient mechanical energies. And then self-powered muscular monitoring system, and then self-powered impact sensing, and multi-layered hybrid nanogenerators are few of the specific research which we focus towards application oriented. So first let's see about the recent progress in electronic skins. So since we are going as a wearable device, so we call it as a skin, like a secondary skin. What they do, why we call it as a skin? Because what skin do is, so the skin starts to sense. It's one of the external stimuli or the first way of response which sense what we are getting, any kind of impact we are getting. So these skins, electronic skin, what they are going to do is they started to respond to any kind of mechanical stimuli which it gets. For example, it starts to feel the sense of touch. That means if I am making an electronic skin and put on the hand of a robot, when you give a handshake, the pressure which the skin applies, the skin receives, there will be a small strain deformation occurs. So what happens when there is a change in strain? It's one form that there is a pressure which is induced on the skin. So the robo will feel the sense of touch, that there is a change in pressure, that means someone is touching me, or someone is giving a shake hand. Like that kind of a response, it starts to receive. After that, what the robo will do, when the signal transmits from here, the skin to its signal processing unit, it starts to proceed further. The next action. So that's why we started to call it as an electronic skin, or the secondary skin on a skin. So mostly they have several applications, like one I say pressure mapping. So pressure mapping. So mapping in the sense, there is a one big electronic skin I put like a layer, assume. So here I divide into several segments like array. So each segment will start to do a corresponding response. That means when the entire segment receives a pressure, so that means I program like when there is an entire skin receives a pressure, you do this specific task. When 3 or 4 of the segment receives a pressure, you do this specific task. Means raise your hand, fall down, like that kind of a command I can able to program. That's why it is like pressure mapping. Then force sensor, temperature detection. Of course, you can able to how you will identify your body temperature through your skin only. So again, this mimetic skin will respond to temperature. Prosthetics are like robotic hands and arms or limbs which you can use for rehabilitation. Human machine interaction, which we and any kind of a machine which we interact through this kind of skin. Health monitoring. Of course, when I put a skin like this, even your heartbeat or your pulse can able to beat like this. So that means there is a deformation in the strain or stress response which we get, can able to give this kind of a signal. Because the best example I can say is, when you go to, typically everybody would have taken ECG at least once in our life. So they put a small patch of electrode only. They just apply a gel, they stick one electrode. On the top only they will attach the wire. So that itself one of the wearable device only. So which we are using. So what it do, it directly calculate the heartbeat. Or when they put the device here, it directly try to recognize the pulse. Even we put our pulse oximeter to check how much the pulse we are getting and everything. So that is a bulky device. But through the electronic skin, we are reducing the bulkiness to a thin layer. So that is what the major advantage is. Like you can see here that biomedical sensor are there, and then you can see integrated circuit. The integrated circuit itself is coming on the thin layer. So several applications. So these are all the recent progress. So one example which was published here by my collaborator lab, what they have done is like stretchable and transparent triboelectric nanogenerator as a tactile sensor. So tactile sensor is like it can be able to scavenge the mechanical motions. What we are doing. So that is kind of a tactile sensor. You can see this is one tactile sensor. There is a sensor here. Sorry. On the skin. It's transparent. So that's why we will be able to see. So this device, here you can see it very well. They put some 9 segment over it. So each segment will do a corresponding function. Maybe here what they have done is they have gone for a touchpad. They have made a 3x3 pixel tactile sensor, so 3x3, so 9 they have put. So that means I am controlling a remote car. So in the remote car, I put a tactile sensor like this way in the 9 segment. The first button corresponds to the car move forward. The last button corresponds to the car which can come back. The left and right corresponds to go left and right. The middle corresponds to brake. Like that, if I put a logic here, so I can able to control, or I can use this sensor as a remote. Just nobody knows that I am having a remote or a sensor in my hand, but it will be like mimicking my human skin. So that kind of. So here, the same stick has been put on the arms. So when he stretch and release, so it started to give the electric signal output. That means that can be able to scavenge the mechanical energy what we are giving. So using this also I can be able to specify or do several other applications also. So like is holding, releasing, all these can be done with that. So again, this is one other. So this is like a strain sensor where you can see the device has been fabricated. So here AG nanowires are used as one layer of electrode, and copper, this yellow color, this corresponds to copper. Copper is where we can able to take the lead out, and then silicon rubber is there. This silicon rubber is one of the negative triboelectric material. So what happens is, our human skin is there, the skin is a positive triboelectric material, silicon rubber is a negative triboelectric material. When this positive and negative material start to interact with each other, with the friction, there will be a charge transport which occurs from this positive material to this negative material. So leading to development of electric potential here. Okay, so that is what they have made that one. Using this approach, they made a device which can be gone like a origami shape. So that means they cut like that. So you see that origami, like you can pull and release, right? That kind of a structure has been made here. So and then they have studied the performance. So this acts like a supercapacitor also. So they charge it and discharge can be shown through an LED. And here it can be directly used as a wearable device. So they power their wristwatch. They have, you are having a wristwatch, right? So that wristwatch have been powered by wearing this device on the hand. So when they are going for a jogging, so that time you will be moving like this. So the device would undergo friction. It produces electricity. Directly the wristwatch could be powered from that. So now this is again another one. See here, they made one sensor out of a skin. This is a single diagram where you can see here how they put it on the hand. Here exactly you can see. The schematic of that picture is here. So one part is acting like a solar cell, whereas the other segment is acting like a strain sensor. So when they are going out, when this device gets exposed to sunlight, so it started to work like a solar cell, and when they are able to bend and release, so that time it started to work like a strain sensor, started to detect the different ratios of strain. So when there is a solar cell inbuilt on it, even instead of putting a thin level strain sensor, even if you put a commercial electronic device, that device also would be powered up. And then again this is one other application. So fiber based wearable autonomous energy harvesting and storage devices. You see that how the impact of this research. The previous work got published in Nano Energy, and this work has been published in Science Advances. So this is like the fiber shaped device. So what they do is, they take two different fiber yarns. So one of the material, copper. So copper yarn which is acting like an electrode. So they took the other two material. One would be of one polymer which have negative triboelectric coefficient. The other would have been a positive triboelectric material. When these two materials start to create friction, so the charge will transfer from here to there. The transfer of charge is nothing but your electricity. So in a fiber they have done that, and when you do hundreds of fibers and when you knit it, you can make like a cloth. So that kind of a structure has been taken and that has been worn on here and here. So when we walk like this or do like this is the place which we get the friction at first. So what happened, the places started to get the friction and eventually they started to generate electricity out of it. So now present day scenario and future scenario would be like this. The present day is the first generation devices that what we are using at our present day. We are using the smart watches, smart gadgets, virtual reality glasses that we are putting and playing the VR games and experiencing some kind of a VR experience. What we can able to do in reality, we are doing it through the VR glasses and Apple Watch and everything we are using. So again, the first generation sensors. The first generation sensors are what that we are using present day. It's like the watch have a sensor which can able to count the number of footsteps that you are walking, the number of steps that you are running, and your pulse level, your ECG electrodes which detect all are first generation sensor. Now with the introduction of this wearable electronic concept, that too flexible and wearable, although they are wearable, but still it's a first generation device. Why I am insisting more on that? It's because they are bulkier in size. Okay? So when you go for this next generation devices, these devices would be directly worn on your hand or you can wear it like a cloth. So this is, so now there are some research which is going ahead, like athlete monitoring, sports monitoring, like. So what they do is their jersey or the t-shirts that they are wearing, right, on the t-shirt itself, knitted sensors or wearable sensors are coming. So how long they could be able to run, what is his capacity, and everything can be calculated using that. No need of a bulkier device to put it on the hand or in the dress. You might have seen that in cricket what they do, suppose like some guy is doing a bowling action which is illegal. So what they do is they put a number of sensors on his body and they will ask him to bowl in a separate room like this. So what they will do there is to calculate that they put number of cameras around. So when they put the camera around, when they put the sensor and the camera around, so again there will be a concern called privacy. So you can't do like that, right? So when these kind of sensors which is coming like a t-shirt, you can directly wear on it, no need of camera, remove all these cameras and bulkier devices, some kind of bulky devices when you wear, so your body movement or force would be restricted because of its weight. So for example, there is someone who is like paralytic or they couldn't able to, someone's hand or limb have been broken due to their accident. When they get rehabilitated to recover from that, these kind of sensors to be able to predict very clearly or easily about their various stages of rehabilitation. Whereas the prosthetic limbs are presently used, they are heavy. Someone wear a robotic arm or leg, you try to lift it, so that weight itself he could not be able to want. How we can able to predict it easily the degree of rehabilitation. So the next generation devices are going to be on-body wearables. Few products are already coming out, so still the power source is one of the major problems here. So this is what I insisted, like the remote operating car, so which is there, which is going and coming. So there is a wearable device which is made of polyurethane dielectric material and PDMS substrate. So polyurethane is one kind of a dielectric, PDMS is another kind of dielectric. So when the friction creates the signal produced, the signal is used for driving this car. So here you see the device is worn on the hand and here the car is able to control. So what is there in the normal condition, the device can be able to produce this much volt. When he touch, there is a change in strain due to which the generated output is reduced. And when the more pressure is applied, again there is a change in more strain which relates to the reduced electric output. Again when he released it, so it goes back to normal position where you can see the output varies. That means this works on the concept of change in the amplitude of electrical response with respect to the touch that we are giving. So this is also a tandem organic solar cell. So this is also could be able to integrate it on the human skin. But on the various layers they can able to put, that layer also can be put in a very thin form. So that is how. So like array of devices which can be put here. This is again piezoelectric. So piezoelectric array of device. So what happening here is the different degrees of finger bending motion. So the different signals can be able to track. Here the device is on the palm. So which is very transparent where we cannot able to see the devices on the hand arm. So this is like the graphic based tactile sensor device. So now we saw about the device, the wearable electronic device. Now we will go like why we need these kind of a flexible power source. See, first of all, like the energy required that we are using it in the transportation, portable electronic and our home appliances all are now having more and more electronic components. The devices are become intelligent every day. So even now, take example of automobile. So in automobile, earlier we were driving the car which doesn't have much of the electronic component. But these days what happened? Airbags are there. When there is a collision occurs, so it was detected by accelerometer and your airbag gets open. Then when you are not wearing your seat belt, you are getting alert. You are getting alert. Now what happens? Still more, you can able to close and open your side mirrors by simply pressing a button. And again, where sensors are playing a role, track identification. So where you are going in the car, in the road, so if you are missing the white line, the car will be able to get track of the white line and automatically the steering will move to make you to adjust to center. Hill hold assist, that is also sensor which will directly apply a brake for a certain second to protect. So sensors started to play their role everywhere. Now your car is getting intelligent and your portable electronics, you see earlier the computer was in bigger size, now rarely people are using desktop. So computer size reduced, laptop comes, then even the laptop size started to reduce, palm top level, your mobile phone comes, mobile phones are coming with sensors, gyroscopes are there, accelerometers are there, so many sensors are there, even your phone can able to detect your heartbeat and your pulse rate, sensors. Again, this power consuming devices, like power consuming in your electronic appliances, your AC is there, you would be connected to Alexa or something, you will say Alexa turn on the AC, so it will turn on your AC. So you say Alexa turn on this TV, you are turning it on. So again sensors started to play a role. So what restricts its miniaturization further is the battery or whatever you are using for your wearable devices, because batteries are bulkier in size. So before going to that, we will see this slide, the global power requirement from large scale to small scale. So again this also matter, because what happened, now the devices are getting slim and we are coming into very tiny level. So here one good example is cardiac pacemaker. This cardiac pacemaker we have started to place these days into our body. So what happening is, this cardiac pacemaker has battery in it. So once a person have a cardiac problem and the pacemaker was fit into his body, so that will be functioning for few years. Suppose the person is very healthy, is doing good, the cardiac pacemaker battery have gone, the power of the battery gone. Although that person is healthy, he need to go for one more surgery just to replace that battery. So what happens? Again it is risky for the patient. Suppose if unfortunate cases something may happen to the patient, again he need to spend 2-3 lakhs or some amount of money to go for the surgery, need to be bedridden, and so many complications are there just to replace a battery. So now batteries, however, they still have some other drawbacks, like they heat when you use for a prolonged period of time. It requires frequent charging. And simply if a battery is completed, you may also have heard that some of the phones have been blasted because of their battery overheating, that kind of a problem. So if there is a battery which have been completed, any battery, for example the wall clock, typical example you can take at your home. If the wall clock battery have been completed, you will just replace the battery, but where you are discarding your previous battery, we are simply throwing into our dustbin. Actually it is an electronic waste, it has to be discarded separately, but we are not discarding like a separate waste, rather we are putting it into a normal waste. So it is again, sometimes that battery also may burst, sometimes that battery also may leak out some acids or some kind of a toxic material. So dumping e-waste is again one of the problem, and then these dumping e-waste are again toxic to environment. Suppose there is a river near, so I just replace a battery and simply if I throw inside, maybe someone may do like that, again it is again toxic to the environment only. So it's not like all people do, one and one do, that means we will pollute slowly, so harmful to the soil, environment and the aquatic systems or animals also. So that's why people are looking for a proper replacement of a battery to go for this kind of on-body or waste mechanical energy harvesting technology. So although we are going for a renewable energy harvesting like solar cell and everything, but they are bulkier. They can able to power our buildings, household and our appliances. But what the other problem is, portable and wearable electronics are increasing day by day. Now we need to think a possible way to power low power electronics by replacing the battery. So that's why we go for the self-powered concept. Now plastic electronics also play into it. So this plastic electronics are, one is like flexible solar cell, then flexible energy harvesters like triboelectric and piezoelectric nanogenerators, and then electronic skin. These electronic skin is directly connected to IoT based systems. So what? They are very simple to develop, high power to weight ratio, higher PCE, mechanical durability is there, and low manufacturing cost since you are going for a low power system. So triboelectric nanogenerator with wearable, they are very easy to fabricate. Depend on the material we use, we can make eco-friendly material also. So readily adaptable, simple and fast, cost-effective and robust and durable. You can use for any kind of an application ranging from human-machine interface to artificial intelligence-based applications. So as per the law of energy conservation, so energy can neither be created nor be destroyed, but can be converted from one form to other. So that's why the most abundant energy is mechanical energy. So even if I walk, I create a mechanical energy. So I am walking, so there will be energy which is produced. Work is done, work is I am moving, but some energy will be wasted. Without an energy conversion, there is nothing happen in this world. Whatever we do, some energy will be released from it. See, the best examples are our heart beats, that is also a mechanical energy. And then again we can see wind. Wind is kind of a mechanical energy. Our blood flow is also a mechanical energy. Vehicle, number of vehicles are moving, billions of vehicles are moving in the world. Even if I put the energy harvester on the speed breakers, whenever the car passes into it, that energy can be scavenged and can be stored in the battery, where I can use to power the roadside sensors or traffic signals also. That kind of a possibility is there. That's why mechanical energy is one of the most abundant energy source, where we can be able to easily convert that to the useful energy. Here see this journal, Scientific American. So this is one of the very popular journal which was talking about solar energy. By 2050 to free US from the conventional power source. US in 2050 they will be completely go beyond solar power. Whereas the article is saying in the next line, self-powered nanotech. Nano-sized machines still need tinier power plants, where you can see the cardiac pacemaker is there, which is connected to a triboelectric nanogenerator. So, which I say earlier example of, you want to go for a surgery just to replace a battery of a cardiac pacemaker, if we put an implantable biocompatible nanogenerator inside it, our heartbeat mechanical energy itself can be able to produce the electricity and it can power the pacemaker back without going for a surgery. Maybe the surgery may be required, but it might not be that much frequent as per what the battery based system. So that is why this field has been gained huge importance because of its application in implantable sensor, patient monitoring, environment monitoring, Internet of Things, some kind of a security system, asset monitoring and everything. So you can see that n number of examples with the wearable technology, ranging from beauty sector, cosmetic sector, styling, fitness, sports, wellness, medical field. So many biomedical sensors are coming out of these kind of wearable electronic devices. Now let's see more close about this nano generator, which started in 2012 with 3.67 of milliwatt per second, which was the first device which was fabricated in 2012. So that device, that paper was published in the first issue of Nano Energy in 2012. The paper title is Flexible Triboelectric Nanogenerator. That's all. So if you guys had a chance to see, you can see that one. So that time they have started the contact separation mode thing. That means contact separate. Like that only it will work. Then in the next year, lateral sliding and single electrode mode of the triboelectrification was improved. And then again they go for several kind of applications. Now then they use for bionic thing, wireless, blue energy harvesting and so other applications. Now this field, they started to obtain watt per meter square kind of a power output also from this and have been used for several applications. In piezoelectric nanogenerator, as we are very well know about the piezoelectric effect, the ability of material to generate electric output upon getting any mechanical stress into it. Very well known material are zinc oxide, barium titanate, K and lead zirconate titanate. These are very well known piezoelectric material, and the device which make out of this is piezoelectric nanogenerators. So in that also tribo or piezo are there. Again hybrid generators are there. This hybrid generator, what they do is, one of the tribo layer is replaced with the piezo material, where it can able to harvest both the performances. In simple word, so far we talk about tribo, but still simple way to talk about tribo is you could experience such kind of a phenomenon in your life at least once in your lifetime. Like in your school, we do like rubbing the plastic scale on our hair and try to pull the paper, which able to do. That is static electricity. That is none other than the scale is there. You pull some electron from your hair. The scale is plastic. The plastic have negative material. The hair is positive material. You try to pull some electron from it. That electron comes to your scale. When you put it on the paper, which is another material which doesn't have much electrons, so it will start to attract that one. So this is like a typical triboelectric series where you can see this rabbit fur, our hair, nylon, all these are having positive in the triboelectric series, and more of the polymer materials are negative in the triboelectric series. So triboelectric nanogenerator is like you are scavenging that energy by putting two electrodes on both of the triboelectric layers and taking the electron out of it to power something out of it. That's what. So again there is something called the surface roughness here. Here you can see one surface is very flat. The second surface you can see there is multiple roughness, surface roughness. What this surface roughness do is surface roughness enhances the contact point. Thereby you can able to multiply the electrical output which you are producing. So if there is a flat surface here in the bottom, that means top flat surface, bottom flat surface, that means single contact point only will be there. When the surface roughness is more, the contact point multiplies, thereby improving the electrical output. So this is one of my research article which was published in nanoscale, and that came as a cover page of that journal as well. So here what we have done is self-powered muscular monitoring system using piezoelectric composite strip via a groove technique. So here what we do is a simple grooves we have made in acrylic sheet. We try to put titanium wire in the middle. The titanium wire itself will act as one of the electrode there. The piezoelectric composite polymer was poured into that groove, and then we have cured it. When I peel it out, a strip kind of thing will come where there is a thin titanium wire which will be an electrode inside. Here you can see the FDSM image here. You can see I made a groove, so the flat surface with groove is here. Here I put titanium wire as one electrode. You can see the wire is popping out. PI wire. So that means the first electrode is ready here. What I do for the second electrode, now I bought a commercial adhesive bandage. On the top of the bandage I put the strip here. This is the composite strip. On the bandage I attached it here. You can see it. The bandage is there. Here I put the strip. I use silver paste as another electrode which I coated. One electrode is titanium wire. The second electrode is silver. Now you can see here very clearly how lightweight and how much twistable it is. So on this I soldered with one wire. The TI wire is there. There I soldered and take out one more copper lead. So now two electrodes came. Perfect piezoelectric nanogenerator is ready. So I produced 3 or 4 different devices out of it to reproduce whether I am getting the same result or not. So I could able to reproduce what I am getting it back. And then I have attached it on the fingers of the gloves. So now what happened when I start to use this gripper or any kind of a finger motion, so I tried to do like this, so it started to respond for that. So this is one way I proved that this can be used for any kind of a muscular monitoring application. Then I put it on the different places of my human body, like on here, neck, leg, everywhere. And then we started to do this kind of a muscular motion monitoring. be able to recognize even the simple movement. Here this is breathing, so I put it here and I start to breathe by mouth like that. So then I could be able to recognize the breathing pattern also out of it. And it can able to produce when I touch with finger, so I connect to a LCD display where the display started to pop it off. So the next one is again we go for one impact sensor. So here we have used barium titanate. So the barium titanate I made it like a porous composite film. So I created pores on the composite film. Why I go for this approach is the pores can able to trap charges into it. Because when I apply pressure on that one, this pore also can able to go for a contact and separation where some of the charges can be trapped and the trapped charges will be eventually released so that there is a chance to increase its output. So you can see the FDSM image here which very clearly shows the micro-sized pores which is on the film. And then I used it as one of the layer and fabricated the device out of it. And I have checked the electrical response. Here I analyze the charge, you can see here. This is a dense film and the red color graph corresponds to the porous film, where the dense film started to store in different acceleration with a maximum of 10 nanocoulomb of charges, whereas the porous film started to store around 18 nanocoulomb of charges. So when there is more charges which started to accumulate, when you try to generate an electricity out of it, the electrical response also will increase. So that is what we are showing in the electrical response here. So here, this is a typical response of a piezoelectric device, where I even analyze the single peak also, that how the device could be able to respond for it. So here I combine with the piezo and triboelectric effect. You can see the piezo device is giving few voltage only, like around 10 to 20 volt, and a current of few nanoampere. When I go for a hybrid mode with the tribo, so I am seeing that the multi-volt increment is there. The voltage is almost going close to 380 volt and the current is going around 4 to 5 microampere. That much of increment. So I again try to charge a few commercial capacitor to validate whether the electrical response produced from my device is not noise. It is the electrical response. That we can see these capacitors to be able to charge my device. Even a 10 microfarad capacitor have been charged to 0.5 volt out of which. So even here you can see a 2.2 microfarad capacitor with a hybrid mode. In 100 seconds I charge to 2 volt. So this we have driven to several other applications by powering up LED. Even I powered up a wristwatch also using that one, the power which I have generated. And then we go for an application of impact sensor. So this application was a simple proof of concept. Now in our lab, they are extending this application towards connecting it with the IoT based devices also. So what we have done is a bicycle helmet we have taken and we put nano generator device on 4 different sides. Now what happened, a guy who is going for a bicycle race or riding a bicycle, so if he fall down, suppose he got a hit on his body. Now what happens, when he fall down, his head got hit into the floor, there will be a signal produced from the nano generator because the device will get actuated. That signal is sufficient to show the impact of the hit, because you see we have performed a force analysis. When the ball dropped from 20 cm height, the device generates very less voltage. When the ball was dropped from 100 cm height, the electrical response was 30 to 40 volt. That means if I fall down from here or if I fall down very fast with a high impact, the signal which produces will be very. So based on that, the medical team or the physiotherapy team who would be sitting on the match, who would be aiding or supporting the players, they can be able to recognize where the hit had happened, how much impact he have received the hit. So that means whether he can be treatable here or we have to rush to the hospital immediately. Those details could be predicted very easily. If the patient is awake, he can say that it's a mild or what. Suppose if he go for unconscious, or even sometime I say nothing happened, I am normal, but there would be a heavy injury which can be shown later on. So based on the impact of the hit, the doctors or the medical team can be able to predict or analyze the scenario immediately. So this is the proof of concept only we have shown here by simply hitting it with the ball from different directions on the helmet, and we have taken the result. But this one, now we are again further analyzing with IoT devices to modify this application or extend it to the further level. So next we again go for a concept of multi-layered piezoelectric nanogenerator. So here you can see, here we have changed the device design. So to go for a multi-layer. So here every layer we have kept a device. This is device 1, device 2, device 3 and device 4. So 4 devices could be operating in a single structure. So that means the output will start to multiply. So this is the typical working mechanism, that how with regards to the application of force, the electric output generates. So where you can see that this is with the individual device. This is how much piezoelectric nanoparticle into the polymer. We optimize the weight ratio of the polymer to piezoelectric material, and then we have studied with respect to coding analysis of the piezoelectric material. And then here we have seen that individual piezo tribond hybrid effect. That hybrid was showing a multi-mode electrical output. And here 4 devices were there. Here we connected the 4 devices in series. So 4 devices in parallel we have connected. So where you can see that the voltage response remains constant, whereas the current started to increase with respect to every device which it gets actuated, because all the 4 connections were taken and connected into parallel. So parallel connection makes the voltage to be constant and current to be increased. So here we can able to charge a 10 microfarad capacitor also very fast, because of the number of layers which increases, so that the generated electrical output is very high. So here also we can able to power few of the LED, some commercial lamps and calculator, and then the watch. And finally we go for one more application of attaching it to our human body, and we started to do different exercise or yoga pose. So like whenever I go for a push-up, so when I bend and release, the device starts to move like this. So that means I do repetition 1, 2, 3, it starts to count. So every time when I move, bend and release, it leads to producing one signal. So that signal will start to count using a counter circuit. And here I go for a remote control using an infrared LED, where I remove the battery of the remote control and then I put the nano generator into it. So when I start to press this, the LED start to glow, and there is a fire alarm which we have kept here. This fire alarm circuit, what is the thing is, like this kind of fans are there, right? These fans will start to rotate, producing the mechanical energy. A small movement where the rotation energy converted to linear motion. So this, whenever the fan is rotating, the linear motion will start to actuate the nano generator devices. So that has been connected to the fire alarm. So now what happened, the moment when I put the fire near to that fire alarm, so it started to blink the LED and the buzzer started to beep. So it's like completely I deactivated that fire alarm from the electrical circuit. Rather the power has been given only from the nano generator we fabricated. So this is one of the very good proof of concept that the low power electronics, even the commercial electronic components could be powered with this nano generator. So finally we studied several approach and go for commercialization of nano generator. So one approach is like a waste material usage. So this is a typical waste material what we had in our laboratory. So what we did is, the waste plastic cups are there. So we have taken all these waste plastic cups and they were using a hot press. We hot pressed it to form the thin layers. On the layer we took the tissue papers which we wipe and we throw in. All the tissue papers have been collected and then I soaked in water, and then again I made it like the cellulose pulp. That cellulose I made it like a paper bag. So now again I am recycling the laboratory waste. One is this waste plastic lids I made as the substrate, and the carbon cloth I put it inside. This material has some PTFE on the cups. That PTFE has also been taken, melted, and then I made as a layer. Now the paper is a positive material, this PTFE is a negative material. I started to actuating this, where I could be able to produce 15 microampere of current. and I produced even higher electrical output from it, out of it. So the current was very high. So what we did is I go for an application. That application is like a wearable application. So what I did, the triboelectric device I have taken, I covered it with the paper and I made like a wristband, I put it on the hand. So all might have heard about the Morse code transmission. This Morse code is none other than, suppose if we are isolated from all the communication, only the Morse code will work. So this Morse code only military people also will use to transmit some kind of signal. So that signal will be like, for example, you want to send A means dot and dot, like that only that will be there. One dot, one dash. That means one short beat, one long beat. Like that the Morse code is there for numbers and alphabets. So that kind of a Morse key we started to transmit here. So Morse key transmitted, it was used. So here and then we used one touchpad. One 8-segment display we have taken. All these display keys were made of nanogenerator device, which is made from waste. When I start to actuate it, I can able to see different display here. Here I have a video where you can see this video also. Yeah. So here, whenever I touch the keys, so you can see that the segments start to display. So this is 0. So this is the letter B. Now number 1 is displayed. The thing is, we would be having keypads or keyboard, but the keyboard, what you will do, you will connect it to the power supply to take power only. Using the power only we are doing. But here what is happening is, the power is generated from here, only signal is going, not the power which is consuming. Even take a wireless keyboard, you have to put battery into it first. But here it's not the case, rather the signal itself started to do this application. So I started to dial several things. So using this I can transmit Morse code, using this I can able to transmit some kind of a code words or signal out of it. So this paper got published last year in AC Supply Electrical Interface for the idea of waste recovery and the application. So the next one is the waterproof device. So this waterproof concept also, the device is open layer, right? So they are prone to humidity. So even the humidity condition or the temperature of this room would be different. If I go out, it would be different. So the humidity can able to affect the performance of the nanogenerator. So we go for a fully packed pen device where you can see the device was a simple encapsulation technique. And here you see in this, I put into a water tub and then I am actuating the device. The device is working very good condition. No water penetrate inside. You can see the device can able to generate electric signal out of it without any interference in humidity. Where the below it here, this you can see that from 10% humidity, 42%, 68, this is 48, 68 and 99% humidity. I created a small humidity chamber, I passed humidity into it. The device is giving stable electrical response because of its encapsulation. And you can see from the video that even I put it on a water tub and I actuate the device, but still without anything, it's working like a water resistant. So this paper got published in nanoscale advances, and you can see that the power which is generated from here can able to glow these many LEDs. So here I am tapping the device. So where this is glowing, around 50 LEDs I have connected here. So all the 50 were glowing in very bright conditions. And then actually here the thing is, you can see that the device is producing somewhat around 200 to 300 volt. Even one of my device produces 1000 volt also. But the problem is current. Current is only few microampere, 2 or 3 microampere. So if we want to power any of the component, 230 volt is sufficient. But you need current more. But here, for powering the low power device, this is sufficient. Although if we want to be much more towards commercialized, then this is more important parameter to configure. So So that's why we go for a concept of hybridizing this nano generator by coupling with the electromagnetic generator. So this is one application that we have done. It's like a flutter based device. We made a small wind tunnel here. So the small wind tunnel, what we do, so we have made a small thin Kapton film. This Kapton film, if I hold like this, in wind it will start to flutter like this. So this Kapton film, I use inductive coupled plasma etching to etch one side to create more roughness. On the other side I put aluminum. When this started to flutter in wind like this, it will start to create friction. So when it is creating friction, I put one small, take a thin coil, I have mounted that coil and attached on one side and kept the magnet on the top. So now this coil starts to go and interfere. So with the magnetic field, this coil will start to induce flux and started to produce electricity. Now what happened? Electromagnetic generator generates high current. When the frequency is very high, it starts to generate more volt and current. Rather, in case of triboelectric nanogenerator, it produces more voltage. Now combining this two effect, I started to match or overcome the problem which I face with the current. So now electromagnetic generator produces more current, triboelectric nanogenerator produces more voltage. So as a result, I started to make a small windmill kind of a thing. I put 4 wheels under that and kept one small wind vane so that when the direction is there, the wind will hit here and this tire alignment will make it to rotate. So whichever direction the wind is there, it will start to work. So for safer side, I put 4 different directions, 4 devices. So whichever direction it is turning, 2 devices will work, 2 devices will be idle. When the wind direction changes, it will start to rotate, the other 2 devices will work, the other 2 devices will keep idle. For example, if I want to do any sort of maintenance, so when there is the other wind period, I can replace the layers or I can do anything out of it, wiping out the humidity or whatever. So with this, I started to monitor the direction of wind. Simple. I put 1, 2, 3 and 4. If wind is in this direction, 1 and 2 will work. If wind is in other direction, 3 and 4 will work. So then I can say wind is from east to west direction or wind is from north to south direction. So even wind is in the northwest or southwest, it will turn to the automatic direction because we put the wind vane and the tire right. So up to that level, it will start to rotate and it will start to operate. So for that identification only, I kept the LEDs on all the sides. Whenever it starts to flutter, this LED will start to glow and show the produced energy is getting utilized over there. So this is what I told them. I do plasma etching, the inductive coupled plasma etching under different atmosphere. So I created several micro roughnesses on the film. So when I talk about triboelectric, I say that the roughness will multiply the output voltage. So that means in concentration 3 that I can see 60% of oxygen and 20% of argon. When I passed through that etching, the roughness was very good. So this produces high electrical output here with the triboelectric. So that's what I optimized with the plasma etching here. And then we can see very clearly that only EMG is producing less voltage, only 10. When I hybridized, it started to go for very high, where I can see with respect to wind direction, so and wind speed, how it is going. Because what happened when I put the 2 different supplies, one electromagnetic and triboelectric into the same circuit, there will be a transient mismatch happen. So that's why I rectified both the tribo and piezo output. The rectified output only I used it for the application. Then again using that I started to power up few LEDs to show the demonstration. And here also one hybrid nano generator we fabricated. So what that do is, it is like this kind of a buoy shape. This buoy is kind of a floating device which will float on the water. So here I put one triboelectric and electromagnetic hybrid. So here you can see the typical device like this. So here you put a magnet into it in the middle coil. So when I put magnet there and started to move like this coil will produce electricity. On this last 2 sides, I start to put 2 triboelectric layer. So when I move like this, the system will hit left and right of the block and the magnet will start to move in the middle. The magnet will produce electromagnetic and both the corners triboelectric output will start start to produce. So by that way, here you can see I kept one device here. This is a LoRa device. LoRa is like a GPS. You have a GPS into it, it will start to detect the position. So this work has been done when I was a PhD student in Korea. So that time few undergraduate students come to us to do their undergraduate project. One of the guy was from a fisherman family. So he told that we want to do something like the fishing net tracking system, like that. So for that only this concept was designed. This is one single device, one single small unit. Then we scale it up after checking the proof of concept with single device. Here you can see a big buoy was taken. Here only one unit was kept in the middle as shown in this figure. Here multiple units we have kept it after doing it. So on the top we kept solar panel. Why we kept solar panel is in sea we can see that there is a rough and soft condition. Sometimes waves will be very high where you will be having more deflection. Sometimes waves will be soft. When high wave condition, the device will actuate, more mechanical energy will be there, magnet will move, the triboelectric will also produce. Whereas in the soft condition, there won't be much movement. So the solar panel will act as a backup. So this position sensor will start to detect the position. Here you can see very clearly the electrical response we generated. This is with the electromagnetic generator. At 3 meter per second and 5 meter per second, you can see there is a increase in the output. You can see it produce tens of voltage only, whereas the triboelectric components start to produce peak to peak 200 volt. But current is very less here, but electromagnetic generator current is around 30 milliampere. This is only 5 or 6 microampere only. So voltage is matched here, current is matched here. And this is the response from solar cell. The solar cell is only for backup. If these two hybrid components are not working, then solar cell will start to power. And then this is what the real-time application we did. I told right the bigger one we have made after making the proof of concept. Bottom are the triboelectric layer and EMG layer. Then we put the middle layer. We kept the LoRa system. On the top we kept 2 solar panel and 1 LED. This LED light will show there is some floating object is there which is floating. So this has been connected to fishing net. And whenever the fisherman put a net somewhere, later they can come and they can be able to detect because it have a GPS inside. The GPS will be powered without batteries. This system itself will power. Backup solar cell will power. In night time when sea waves are there, that will power. Here that GPS application was installed in the mobile phone. So even we put it on the sea. Somewhere on the sea, we went in a boat and we kept it. We came to the university also, and also we were tracking the position. So this below image is the route we went, taking this buoy and we went in the car. So all these positions we were tracking time by time. And again I tried it one more approach. So when I tried it magnet, why not I tried with a magnetic nanoparticle to do the similar effect. So what I did is I took the iron oxide nanoparticle which is behaving with a very good magnetic property. I removed the magnet and I put magnetic nanoparticle into it. And then I mounted the coil. I kept Kapton layer inside. Now what happened, this Kapton layer and this nanoparticle, when it started to get friction with this material, the friction will start to induce triboelectric component, the static electricity. The magnetic particle will induce electromagnetic component in the coils. So this started to create the electrical output, and then I have used it for a seismic detection application where I studied the entire performance and defined the mechanism of its operation in lateral sliding and vertical movement part. And then I started to analyze with respect to different vibrations, like different acceleration. Yeah. You can see that I started to go with 1 meter per second, 2 meter per second, 3, 4, 5 meter per second with respect to the output started to vary. And here in this video you can see that when there is a seismic vibration happened, so here this is vibrating, so it started to say how much displacement it is happening. So I connected it with one LED and buzzer, so that means like a earthquake early morning. So when there is a vibration start to occur, so this starts to detect because it have particle inside. Particle can vibrate fast compared to the rigid magnet even under less acceleration. So that is what we demonstrated here. This work got published in Nano Energy. My final paper in PhD was this one. And then we again focus towards some of the application, move close to commercialization. So one is like wireless power transfer also we have focused it. So that we put it on 2 coils. Earlier we used to have some pouch for batteries, right? So I put 2 coils on that side. Whenever I slide my phone with the battery, in the pouch, so it started to slide to create a friction. So that power only we generated here. So how we have wirelessly transmitted the power, we used 2 RF coils to transmit that one. The other one was putting it on the shoe sole, and while walking we scavenge the power. This normally we have done many times. And the other one is like a backpack. On the backpack also we have put the device, and when we bend, walk or run, we could be able to scavenge the energy there. So which was directly stored into a battery power bank. So you can able to charge the mobile also there, but rather we put the flashlights over there. So what happened if you are going in the night with the backpack? So in the back it will be giving the indication. You are walking, the light will keep on beeping, so that the people who are coming behind in the dark, they can know that some person is walking over there. And here is another application of intruder identification. So that means some intruders are coming, we try to monitor or track the intruder position, right? So here also we kept the 3 different devices here. So whenever the person starts to walk on that one, so it started to produce signal to show that there are some intruders who have passed over that one. That warning could be able to get it. So then we replaced the solar cell into it to make it completely self-powered one without using any external power sources. So that is one concept. The other one, actually this one is like we take the kids' toys. We started to make the normal toys into somewhat a digital toy. So what we have done is these kind of toys are there, right? Where there are some moving parts into it. That moving parts we replace it with the triboelectric component here. When the kids started to pull it and pull down, this will open and close. That is what its concept. We put 2 holes here, we connected to LED and put the triboelectric here. So when they pull, open and close, what happens? This LED will also start to blink. So earlier it was like a normal open close toy. Now we made it with LED toy. Just a small approach where we approached in a way like demonstrator education appliances, a way towards commercialization. Here also it's stress ball. Here with the puzzle, in different positions of puzzle we put the nanogenerator device. So whenever they put the correct position here, so that means here the display will show C, correct. And then on the mouse also we kept the electrode, and when you are able to do like this with the mouse, the friction will be able to charge the battery back. So as a result, the replacement of batteries for a period have been extended, because most of the time the mechanical energy we scavenge, that power itself is charging the battery back again and again to your mouse. So again here we have shown power in the display, even the bigger LEDs were also powered. So this, and then we put on the rubber toys and cut. So this paper got very huge approach, which was published by ACS press release also. ACS published in their YouTube channel. AAS Science also published in that one, and it was granted US patent also for this concept. So far triboelectric nanogenerator was showing us a proof of concept. First time we show that there is a way toy and kids market are there where we can able to commercialize this triboelectric nanogenerator. So that is what with the triboelectric and the wearable electronic device. So ongoing and future trends of this self-powered sensor concept is like the work of energy harvester. So it's not well commercialized, because even though we are showing there is a route to commercialize, there are still many challenges are there which can able to restrict the commercialization. Because I showed that I went for a hybrid approach with EMG, because the current which is producing here is very limited. Only the voltage is high, current is not there. So that's what the promising material is required to boost the performance of energy harvesting. And then highly stretchable material is also required, because plug-and-play material, limits stretchability, so that you put it on the wearable devices. And then multifunctional application, wearable electronic devices, functionality and IoT applications are also emerging, where we can able to fit our device into those applications. Then e-skin devices are also going on these days, but they are also not well commercialized. If we could able to overcome this challenge, this concept is a very good material to be used in the application like robotics, biomedical application, healthcare and wearable electronic application also. So finally, I would like to thank the KLEF president and the management, and then internal funding from the R&D department for my research, my HOD and deputy HOD, faculty members of our EC department, NEMS and VLSI research groups, and all the members associated with the Center of Flexible Electronics and my research scholars. And I also acknowledge my collaborators who are from the University of Surrey, and my professor, Professor Sanjay Deemed, and all my other collaborators and all my funding agency who were sponsoring for my research work. And finally, thank you for patiently listening to my talk on my research for this past period and the last 1.5 years at the KL University. So if you have any queries, then you can contact me. You can ask me now. Later also you can contact me through my email and my web address.
Sir, what are the important things you have to focus for the selection of material?
Actually, yeah. So here we spoke about two concepts. One is tribo and the other one is piezo. In case of triboelectric, so we need to focus more on high dielectric material. The high dielectric constant will enable to generate more output in terms of current, because voltage we can produce very easily. If you rub any two kind of a material, you can able to generate some voltage, but whereas current, generating current is the problem. So that's why we need to focus more on the current. Recently I have come across a paper. They have used calcium copper titanate CCTO as one of the material, where they have shown the material have a dielectric constant of 22,000, I guess. So that material they have shown that they can able to produce 100 to 200 milliampere of current. So one approach what I am thinking is high dielectric constant in case of a triboelectric and high piezoelectric coefficient for the piezoelectric material. Because there are commercial materials like PM1 PT and lead zirconate titanate. These materials have very good piezoelectric constant. Those materials can produce very good electric output. Because we are using the gas lighter, right, in our home to ignite. That lighter also has piezoelectric crystal only. That only producing the spark. But what the problem is, if we are going for this kind of energy harvester, this PM1 PT and PZP, they don't work because they are lead-based material. They are toxic. Lead-free materials, maximum they show 160 to 180 picocoulomb per Newton as piezoelectric coefficient. Then we have to go for doping approach. So the way to enhance the piezoelectric coefficient is one way that you can go for a high performance device, and identifying a better dielectric material will go for a triboelectric nanogenerator with a high performance.
For measurement of piezoelectric coefficient, which one will you consider
D33, because we are going for vertical contact and separation, right? So D33 mode is better. So if you are going for stretching like that, then D31 mode would be better. Mostly if we calculate the PE loop, in that itself we will start to analyze. Then later we can analyze with the piezoelectric coefficient of that material. Yeah, correct. 3 1. D33 meters are directly there for measuring. Where if you make the pellet of the ceramic piezoelectric material and if you directly put it on the instrument with the electrode, it will directly give you the value. But the other way is put it on the PE loop tester to calculate the PE. Remnant and saturation polarization can be calculated. from that also we can derive the D33, but that is difficult. D33 meter can give you the D33 value easily, directly.
So if you are going for, so you have to be analyzing the piezoelectric coefficient.
Piezoelectric coefficient, usually, because that determines the piezoelectric property of the material, right? So, because PCB even reported 700 picocoulomb per Newton also. Giant piezoelectricity, like that one ACS paper, they have reported 650, 750. Single crystal PATI-O3 was also reported. But they were not producing high performance in outside atmosphere. That study have been carried out with the Institute TEM. They have studied with single crystal material. Single crystal material can produce good piezoelectric, but they can't be stable for a long period of time. So with respect to ceramics, then we need to go for analyzing the piezoelectric coefficient.
Which affect the thickness of liquids.
Which one?
Piezoelectric coefficient.
No. Thickness and the coefficient are not related to each other. They are two different parameters. So thickness is like if you go for a spin coating method to optimize that one, or if you go for a tape casting method to go for, because tape casting what happens is like you will have the doctor blades which they by default they will define 50 micrometer or 100 micrometer thickness. So with that you can directly take into the thickness, because all we are fabricating nanomaterial. So thickness doesn't affect in that way.
So what is the difference between piezoelectric and conventional? So maybe material is different or it is different?
In piezoelectric, the thing is your material internal polarization is giving your electrical output. In case of triboelectric, the static electricity means the friction between two layers are giving your output. So mechanism is I am tapping or putting mechanical energy. It's like just an overview is you are tapping, but internally it's not the same. It's different, two different things. Piezo is static. Sorry, tribo is static. Piezo is inbuilt polarization is coming your electrical. So that is the difference. So tribo, any two material can produce, but piezo, not all material will act as a piezo. Only the property. Both separately, because that's why I told transient mismatch or impedance mismatch is the one phenomena which will occur when you put two AC in a single, two different AC source in a single line. So that means when that comes there, that means that mismatch will happen. So before that, if you convert it to DC, so you can put n number of DC source in a single circuit. So that doesn't affect anything. So piezo, first you rectify it, another energy harvester you rectify it, then you put it. After rectifying, you can combine. After rectifying, connect it to a capacitor and start to use it. It will again filter out the noises.